It's a great pleasure to introduce Gianfranco Bertone, he's a very good friend of mine for a long time. And so Gianfranco works in the dark matter, but not like everyone else. Okay, Gianfranco, yeah, let me say that. So Gianfranco is really an expert of all possible direction of dark matter. So he has studied the possible discovery or the bounds on dark matter in all possible experiments, in all possible bounds. So if you need to really ask something about dark matter, just give him a call. Okay? So he's really a world expert on that. So he did his PhD in Oxford and Paris a long time ago. I'm not telling you when because I don't remember.
2004.
2004. So he did his PhD in 2004 in Oxford and Cambridge, and then he went to the prestigious Fermilab as a first postdoc, and then he had a couple of other postdocs here and there, I guess in Europe, but he was very young, permanent in the CNRS in Paris. After that, he bounced in other different permanent positions because he liked to change from time to time. And now he's in this funny institute called GRAPPA in Amsterdam, who is a professor, and now he's a professor there. And today, of course, we will talk about dark matter. What else? And also, let me say that he writes books of outreach, and he just wrote a new one, that is only in Italian at the moment,
For the moment.
but is close enough to Catalan, I guess, that you guys can buy and read it. So let's give an applause to Gianfranco.
Fantastic, thank you. Thank you, Cristiano. Thanks a lot for this very nice introduction. Today I would like to tell you about a new era in the quest for dark matter, and I will tell you a little bit about the work that we do in this institute, the GRAPPA Institute in Amsterdam. What I will do is I will try first of all to establish, what is dark matter, what is the dark matter problem. So this will be the first part of the talk, and in the second part I will discuss why we think we're moving into a new era in the search for this mysterious component of the universe. Just to make sure I understand with whom I'm talking about, how many of you have heard about dark matter? How many of you have heard about weakly interacting massive particles? Okay, how many of you have heard about supersymmetry? Very good, thank you. Okay, so I think I will try and go quite fast on the first part because many of you seem to be aware of that problem. I will start with like a couple of slides of kind of very basic introduction, and then we will move forward, and I'll move on towards the end of the talk towards a bit more technical material, just to give you a sense of the kind of research that we are currently doing, and in particular, as I say in the title, what I think we can do in the next decade or so to understand what dark matter is. Okay, so let's start with establishing the dark matter problem so we're all on the same page. The first very basic thing I want to mention is the question we are interested in is, what is the universe made of? Okay, at the most basic level, that everything you see around you, and around you means not literally around you, but also with the most powerful microscopes, or with the most powerful telescopes, is basically made of the same building blocks of atoms. And if you look inside atoms, you will see that there are even more simple building blocks. In particular, you have inside the nucleons, you have the quarks and the gluons, making protons and neutrons. And then around the atoms, you have electrons. There's a very simplified version of what exists in the universe, but it is fair to say that you can understand the complexity of most of what you see in the universe just by seeing, by looking at the periodic table and seeing what are the different arrangements of protons and neutrons inside the nucleus, and then the hierarchy, basically the orbitals around the nucleus will tell you what are the chemical properties basically of these atoms, how they bind together, and so on. Okay, now the big surprise in astronomy was that, so if you ask an astronomer up to the 70s, basically, what is a galaxy, or even the 80s as a matter of fact, they would come out, they would show you like a picture like this. This is M31, as I'm sure many of you are familiar with, or sort of a sister galaxy. And when you look at it, it's basically a disk of stars and gas rotating around a common center. Now, the new picture that we have of a galaxy in the universe is very different. So when we think about a galaxy today in cosmology, we have a disk of stars and gas at the center of this big gravitational potential well, and all around it you have this very large distribution of dark matter. Okay, so this is not, what I would say is that this is, today, this is textbook cosmology. Okay, this is not something exotic, this is essentially the only way to understand what happens in the universe on on a very wide range of scales, ranging from subgalactic scales all the way to cosmological scales. Now, I will not go, you've heard about dark matter, so I will not go systematically through the many lines of evidence that we have in favor of dark matter, but I'd be happy to, address, questions if you, and certainly, if those of you who will be in the meeting this afternoon, we can go deeper in some of this material. But I would just say that if you bring together, but actually, even if you do not bring together, if you just look separately at rotation curves of galaxies, at things like the X-ray glow of clusters of galaxies or lensing of clusters of galaxies, or even if you didn't have any observations at all about galaxies and clusters of galaxies, and all you had was the cosmic microwave background, basically from all these observations you come up with evidence for an unseen component of matter in the universe. Okay, and I will tell you a bit in a bit more detail what we mean by that. And then if you combine with other cosmological observables, type 1a supernovae, baryonic acoustic oscillations, anything, basically you can build a coherent picture of what exists in the universe that is summarized typically in public and technical talks in this cosmic pie, as it's often referred to, where all the atoms we just described in the first slide contribute only 5% to the matter energy budget in the universe. 23% is in the form of dark matter, so something that behaves like matter but is not in the form of atoms. And then you have 72%, which is in the form of dark energy. And this dark energy is even more mysterious, if possible, of dark matter. It's not something that binds things together, but it's something that is responsible essentially for the accelerated expansion of the universe. Now, there are a couple of comments I want to make before moving on to more technical material. The first one is that the dark matter problem, many of you have heard of it. You might have been told that this was that Fritz Zwicky in the 1930s, this Swiss astronomer, postulated its existence in the 1930s, and then it's the evidence for it for dark matter was nailed basically by Vera Rubin in the 1970s. What I wanted to mention is that the history of this problem is more interesting than that. And if you look back already at what Lord Kelvin was doing back in 1904, what he was doing was basically he was applying his kinetic theory of gases, so think thermodynamics basically, to gravitational systems. So he was trying to connect the velocity dispersion of stars in a system with the depth of the gravitational potential. And he, just by working out this connection between the two, he argued that many of our stars, and perhaps a great majority of them, might be dark bodies. So I was, thinking about something dark, something invisible, not accessible to the telescopes, that would, have a gravitational influence on the dynamics of things you could observe. And a bit later, in 1906, Henri Poincaré was referring to the work of Lord Kelvin, and even he used the term dark matter to refer to this unseen component in the universe. Okay, and for those of you, I don't have time to discuss this, but we're working quite a lot on the history of dark matter with a professor in the history of science, Jeroen van Dongen, the University of Amsterdam, and with this PhD student whose name is Jaco de Svaat. And I put here in the presentation a couple of references to work that we've done in this direction. So if you have an interest, feel free to ask me questions this afternoon or later after this presentation, or to go and read these articles. So back to this cosmic pie. Sometimes this is referred to as telling us that most of the matter and the energy in the universe is dark, right? But I think it's important to understand that this statement is time dependent. Okay, so there's nothing fundamental about the ratio, or at least not in the most obvious, the most trivial way. There's nothing fundamental about the fact that dark energy is 72%, dark matter is 23%, and 5%. If you look back in the history of the universe, because these components in the universe evolved differently, if you look back at what was the composition of the universe when structures like our own galaxy started to form, so basically back to recombination, where you started to form, to evolve structures from small anisotropies in the universe, then the composition of the universe was very different. Atoms contributed 12% of the universe. Then you had relativistic particles like photons and neutrinos contributing 15 and 10%. Dark matter contributing 63%, so most of the matter budget in the universe, and dark energy was completely negligible back then. So the point I'm trying to make is, well, two, as I said, there's nothing fundamental in a trivial, not at least in a trivial sense, in the composition of the universe today. This is something that evolves. It's like asking, how much water there is on a pan, which is on a stove, right? You get a different amount depending at what time you observe it. Now, it is important, of course, to know in one specific moment, the moment we live in, what is the composition. But if you want to understand how structures grew in the universe from small seeds, so if you want to understand the origins of galaxies and of ourselves, ultimately, we need to figure out what this dark matter is. Okay, and what remained more or less constant throughout the history of the universe was the relative composition, but the relative contribution of dark matter compared to normal matter. So if you just forget about dark energy for a moment and ask how much matter we have in the universe and in what form this matter is, then about 1% is in the form of stars. So if you think about it, when next time you look up at the sky, only 1% of those of stars you see, that's how much they contribute to the matter budget of the universe. Then there is, let's say 14% in the form of gas, between gas in virialized structures and gas in the intergalactic medium. We have quite a lot of control of the gas. We know we can measure quite well this 7% of gas in virialized structures. For this gas in between galaxies is a bit more difficult, although there's evidence that we have detected that too. And then the rest of it is dark matter. It's not in the form of atoms, and we're still trying to figure out what that is. So you might think, how do I believe that this story is correct? There are many lines of evidence that are really pointing very strongly towards this conclusion. But if you want to get a visual impression of how strong this evidence is, you might want to look at numerical simulations of the formation of structures in the universe. So what this numerical simulation is showing is the growth of structures from a universe that is initially pretty homogeneous. And you see here the time elapsed since the Big Bang. And what you see here is basically the density of dark matter. There are no, you don't see any baryons, any ordinary atoms in these structures. And what happens is that if you follow some of these big structures, these are now about 3 billion years after the Big Bang, you will see that something starts to happen in these structures. The growth of dark matter continues to go on, just gravitational growth. But then baryons start to do interesting things. Baryons, atoms, they form stars. These stars explode. They explode and they inject heavier and heavier chemical elements in the interstellar and intergalactic medium. You form black holes. These black holes form jets. These jets, feed back into the distribution of matter in the universe, and so on. And now we can perform these simulations, these cosmological simulations of the formation of structures in the universe, and they reproduce actually quite well the universe we observe. If you do not put any dark matter in these simulations, you cannot explain basically anything. You cannot explain galaxies, you cannot explain clusters of galaxies, and so on. So the question is, if you accept, and I'm happy to tell you more about this if you're interested, but if you accept that all this evidence is strongly pointing to the existence of dark matter, then the next question is, what is dark matter? Right? We cannot claim to have a satisfactory explanation of the universe until we find, we can identify what is this mysterious form of matter in the universe. And I've tried to arrange, the properties that are needed for, a particle to be the dark matter in the universe in the form of a test that these particles have to pass in order to be considered viable dark matter candidates. So the first condition, the first property that these particles need to satisfy is that this dark matter, so this new particle has to match the abundance, the observed abundance of dark matter in the universe. So you need to have a mechanism to produce these particles in the early universe in the right amount to explain dark matter. And this is already quite a stringent constraint, because we know the abundance thanks to CMB, cosmic microwave background experiments, with a precision of 1% or so. This particle needs to be cold, cold is in the sense of it needs to be non-relativistic, so to move slowly at the epoch of structure formation, because relativistic particles would erase structures on small scales, and this is how you can rule out, for instance, the neutrinos of the Standard Model as dark matter candidates, because they're not cold. They're relativistic particles, they would erase structures on the scale of galaxies. It needs to be neutral, so no electric charge, no color, nothing that would allow these particles to couple in a substantial amount with the particles of the Standard Model, with everything else in the universe. And then there are many other requirements. I will not go systematically through them, because it would take me too long, and I want to move on to the more kind of new results. But let me just say that if you just compare, that you get interesting constraints from the analysis of Big Bang nucleosynthesis calculations. So if you calculate the amount of the light elements produced in the early universe, and from the structure and evolution of stars. Okay, in general, the statement is very difficult to introduce new particles in the universe without messing up with it. Okay, you tend up to to destroy stars, to violate Big Bang nucleosynthesis constraints, and so on. Okay, so you have to be very careful when introducing new particles. You want to be consistent with all these experiments. And then there's another line, another row of constraints. We will see some of them later on. But basically, you can constrain really the particle physics couplings, how much these particles interact with itself, with particles of the Standard Model, and the so-called self-annihilation processes, in which two dark matter particles come together and then annihilate into particles of the Standard Model. I will not discuss much more about these couplings. Again, feel free to ask questions if you're interested. And in this test that we put together a few years ago, we also added a sort of a more philosophical point, which is that there should be, in order for a particle to be considered a viable dark matter candidate, it should be at least in principle possible to test it with a type of experiment. Not necessarily an experiment that you can perform now, but maybe when you have sufficient suitable technology, but at least in principle, it should be possible to test the existence of this particle. Now the question is, after you've seen all these constraints, the question is, what is dark matter? And the first thing to realize is that there's no known particle in the Standard Model that satisfies all these constraints. For some time, people thought that the neutrinos, being very weakly interacting, could explain the dark matter, but it turns out that because of the conditions of these particles of dark matter being very cold, then neutrinos are ruled out as dark matter candidates. So you can systematically go through all the stable particles of the Standard Model. You will not find anything that behaves like dark matter. What are the possible alternatives on the table? This is a sort of a mind map of possible solutions to the dark matter problem that have been proposed over the years. The dark matter problem is with us since the late 70s, early 80s, basically, and there's no shortage of ideas, as you can see here. Well, it is impossible to make justice, to this plot in a few minutes. There are many, interesting ideas. Let me just go very briefly through the first nodes of this mind map to tell you, broadly what classes of models people have thought about. One class of models is that of light bosons, very, very light particles. So for those of you who have heard about those, you can think about axions, for instance, or axion-light particles. Then there are neutrinos. So we say, standard model neutrinos are probably ruled out. Well, actually, they are ruled out as dark matter candidates, but maybe you can have something like sterile neutrinos, a sterile version of standard model neutrinos that might do the job. An enormous amount of attention has been devoted to this category of candidates. So new physics at the weak scale. I will say a bit more about those, but if you heard about WIMPs, weakly interacting massive particles, this is where these particles live in this mind map. Then there is the possibility that in general you have other particles, and people have proposed things like Whimperzillas, self-interacting dark matter, superfluid dark matter, and so on. That is made of macroscopic objects, so these macros and machos. There are very stringent constraints on those, but I will mention a few recent results about primordial black holes, because there are people like Cristiano and probably others in the room who have an interest in that. And then there's always this footnote to all dark matter presentations, which is that it is at least in principle possible that we are being misled by all this evidence from astrophysical and cosmological observations, and that instead of sticking to the laws of gravity as dictated by general relativity, we should modify gravity instead. Okay, so we had a long discussion about, a short discussion as a matter of fact this morning with Cristiano. If you're interested about that, I'm happy to tell you more about it. But I think it is fair to say that we are very, very far from having a satisfactory explanation of all the evidence which is explained in terms of dark matter in the universe in terms of a theory of modified gravity. Okay, so we'll not discuss that more in this presentation, but if you have an interest in that, I'd be happy to tell you more. Now, just to give you a sense of how broad is the range of possibilities, let me plot some of these dark matter candidates, and let me organize them, classify them in terms of the mass of the dark matter candidate. And the amazing thing is that you have an uncertainty on the mass of the dark matter particle over 90 orders of magnitude. Okay, I don't think any of us get to see plots where you show an uncertainty over 90 orders of magnitude in science, right? But candidates range from 10 to the minus 20 or 22 electron volts, where you have fuzzy dark matter, these very ultralight bosons, all the way to really huge macroscopic objects like tensor mass primordial black holes. The height of these columns is more or less proportional in a very rough way to the number of papers that have been published on this specific subject. And as you see, there's this tower of models towers of publications that have focused on the dark matter in the form of weakly interacting massive particles. And then I would say that axions and sterile neutrinos are the other candidates that stand out. And there was a revival in interest in primordial black holes in recent years. I will try to get to this later on. And most of these ideas are actually relatively old. They date back to primordial black holes to the early 70s, but the others between the 80s and the 90s. So these are ideas that have been around for quite some time now. Most of you are familiar with WIMPs, so we'll not insist too much on those. Let me just mention, for those of you who are not necessarily familiar with those, is that the idea is quite simple. So if you just ask the question, how can I produce these particles in the right abundance in the early universe? But one of the first things that a particle physicist would do is to try to put these particles in equilibrium with particles of the Standard Model in the very early universe, very hot and dense universe, and then to ask the question how the density of these particles evolve in an expanding universe in presence of these annihilation processes. So this is the Boltzmann equation that regulates the density, the time dependence of the density of these particles. And you see that this is proportional. There's on the right, there's this annihilation cross-section that tells you what is the probability for these two particles to annihilate into particles of the Standard Model. And there's a classic calculation that we always do in cosmology courses where we estimate what is the abundance of particles, the relic abundance of particles that satisfy this Boltzmann equation. And what you find is basically that these particles stay in thermal equilibrium until a certain point, and this particular certain point is dictated by this annihilation cross-section, and then they freeze out. Freeze out means that basically that the number of particles, of dark matter particles in the universe doesn't change anymore. Okay, you cannot transform these particles into ordinary matter anymore. And all that happens is basically as the universe expands is that they're just the physical density will go down due to the increase in value. Okay, if you do the calculation, you find that this relic, in order to get the observed relic density, which is in these units of omega h square, is over 0.1. You get a cross section which is at the weak scale. Weak scale in the sense of really of particle physics. And when people discover this in the 70s, they got immediately very excited because at that scale, they were investigating the possibility that there's new physics for completely different reasons. For reasons that had to do with, really particle physics, the structure of the Standard Model of particle physics, and in particular the so-called hierarchy problem. So why the weak scale in particle physics is so different from the scale of gravity, for instance, in the universe. And they conjectured the existence of new theories like supersymmetry and other ideas to stabilize the weak scale in particle physics. So this was called the Whimper Miracle because there is this apparently miraculous connection between something that solves your particle physics problems, things that you can measure in your laboratory, but also something that happens on very, very large scales in the universe. And an enormous effort has gone in the search for this type of particles, these weakly interacting massive particles in the last 40 years. In particular, if I had given this talk 10 years ago, I would have told you about the many searches that are ongoing at colliders with the so-called indirect detection and the so-called direct detection of dark matter particles. So this is detection of the secondary particles produced by the annihilation or decay of dark matter particles with astrophysical observations, and direct detection is instead really the idea of building experiments that can detect the passage of these particles through the detector. And the point is that despite this 30 or 40 years of searches, no WIMPs, and as a matter of fact, no other candidates for dark matter have ever been found in these experiments. Okay, so this, the big question, and we are transitioning now to the second part of the talk, why this is a new era in the quest of dark matter. We are transitioning towards an era where instead of doing searches which are more guided by a sort of a theoretical prejudice of where we would like dark matter to be in order to solve the big problems in particle physics and cosmology, we need to open up to other possibilities, and I will mention a few examples. Before I move there, I move to the second part. I want to be a bit more clear about the status of searches for WIMPs. So if the question is, are WIMPs ruled out? The answer is a resounding no. Okay, it's if you hear that WIMPs are ruled out as dark matter searches, it's simply not true. Okay, it is true, and the specific point I want to make is that the absence of evidence for a particular particle, for a particular dark matter candidate, is not evidence of absence of that candidate. Okay, this is a sort of confusion that is often made in science and beyond. But let me now make a couple of more technical statements about this to try and convince you that this is not necessarily the case. So the technical statement that I think applies in this case is that it is fair to say that the fact that we haven't observed new particles at the TeV scale, for instance with the Large Hadron Collider, does put pressure on models like supersymmetry and other extensions of the standard model at the weak scale. However, there are still, supersymmetric models, supersymmetric dark matter scenarios, which are still viable. So in terms of fine tuning, and there were, several works that have shown this in great detail. The other, a bit subtle point that I want to make is that the fact of having WIMPs as dark matter candidates is not the same thing as having the WIMP miracle. Okay, so you can have particles at the weak scale that solve the dark matter problem, but not the hierarchy problem in the standard model. Okay, so it's a pity that you kind of break this connection, because it's if you have that connection, it makes it all much more well motivated. But even if you break this connection, weakly interacting massive particles as dark matter candidates are perfectly viable, because they can have a mass that extends up to tens of TeVs. Okay, and I think we should use that as a guidance. If we want to search for WIMPs, we should go towards regions where WIMPs are not the WIMPs that we've studied so far, essentially. And in any case, there's a clear way forward. So for LHC and for direct detection experiments, there are planned runs of the Large Hadron Collider for the next 15 years. So we just accumulated like 1%, over the 1% of the data that we will collect over the next decade and beyond. So it would be simply silly not to search for these extensions of the standard model. And for direct detection, so for these experiments that you build and try to detect the passage of dark matter through them, there's a clear way forward as well, because you can only push the current sensitivity of these experiments by a couple of orders of magnitude before hitting a sort of a fundamental background, which is the background produced by neutrinos in the sun and produced by supernova, the so-called diffuse neutrino background. You start to pick up that signal eventually when you go down 2 orders of magnitude in sensitivity. So there's a clear path forward also in direct detection. I'm happy to tell you more about that, but we already passed half of this talk, and I would really like to tell you more about the future. So this is the current status of what we've done so far. I'd like to tell you more about how we move forward, basically, and what are our best hopes to detect dark matter, or at least to shed light on this mystery. So this is part 2 of the talk, looking toward the future, and I will show you basically 3. So there are 3 broad strategies, I would say, and I want to show you one concrete example for each of these 3. So this is my goal in the next 20 minutes, to tell you about how we can broaden, improve, and diversify the searches, how we can exploit upcoming astronomical and cosmological observations, and then point 3, how we can exploit gravitational waves to search for dark matter. And I'll try to give you one example of each of those. So for those of you who are not familiar with searches for new particles at the LHC, let me show you this in sort of a visual way. The idea is that you inject bunches of protons into pre-injectors at the LHC, and then you just circulate them in opposite directions in the main ring, which is 27 kilometers long. And what you do, so this is the ring, these are the Lagrangians that people write on the walls of the LHC. And then, so basically you accelerate particles in these beams up to energies of 13 TeV in the center of mass. And then you make them collide at the center of very large detectors. So if you have a detector like Atlas, this is an object which is like 15 meters tall, 45 meters long. And then you collect all the secondary particles produced in the collision of these bunches of protons, and you reconstruct the mass and the energy of all the particles and the type of particles that are produced in the collision. One way of searching for new particles is by collecting all these secondary particles and looking for an imbalance in the energy. In particular, what is reconstructed typically is the transverse energy. So there's no, the energy is head-on, so there's no energy in the initial beam in the direction transverse to the beam. So if you collect all the particles produced in the collision and you reconstruct their energy, then you should be able to get something which has zero transverse energy. If you see an excess of transfer energy in a direction, it might be the proof that one particle has been escaping in one direction, like a dark matter particle which doesn't interact with anything else, has carried out some of this transverse energy away from the detector. Now, the point I want to make is that we can improve the way we are performing these strategies and make our best use of data. And the example that I want to show you for this particular search is the use of so-called machine learning methods to extract maximum information from the data. Okay, so this is part of a big project of using or borrowing and further developing some of the methods that have been developed in the context of artificial intelligence to make our best use of data. I will simplify the discussion a little bit here, but feel free to ask me questions if you're interested later on. The idea is the following. Whenever you have a model, so model could be a supersymmetric particle, for instance. Supersymmetric particle is specified by a Lagrangian, your theory, with all its parameters. And what you want to do is to compare the prediction of your model to the data. But data live in a different space. I mean, you cannot directly compare the parameters of your theory with something that you observe in the detector. And the connection between the two goes through many calculations and a code, essentially, that from this theoretical model derives the so-called phenomenology of the model. So, how many particles of a certain time, what is their branching ratios, what are the cross-sections, and so on. And then this phenomenology is injected into a so-called simulator that tells you, if that's your phenomenology, what are the data that you would observe at an experiment like the LHC. Okay, so the comparison between model and data goes through a very expensive calculations and detector simulation. What you can do now, and so this is already kind of difficult. If you want to make predictions for the data, it takes several steps. But people have learned to do this over the years, and now it can be done in a relatively fast way. But you can imagine how complicated it is to go from the data, from something you can measure in your detector, to a theory, right, with all its parameters. So to identify all the parameters of the theory which are consistent with the data that you observe. You have to walk in the parameter space of your theory, perform this exercise many times, billions of times, and then identify the points of your parameter space where the model is consistent with the data. What is happening now, and where machine learning is helping us enormously, is basically you can build algorithms. In particular, we are using something called distributed Gaussian processes, for those of you who have an interest in machine learning, to learn the mapping between the model and the data. And to cut a long story short, you can build plots that show you how the simulated yield, imagine your simulated type of events of a certain kind in your detector compares with the yield predicted with this new approach. And you see that the correspondence is very good. All the errors are under control. You can describe this distribution of points with statistics that kind of make sense and you can keep under control. So this is allowing us to do very exciting things. I don't have time to elaborate much more on this, but I'll be happy to tell you more if you're interested. For those of you who have an interest in the application of machine learning to physics and astronomy, I wanted to mention that we have this new initiative that is called Dark Machines, where that you can register for this and contribute to some of the challenges that have been put forward by our colleagues on this website. This is a community of several hundred people, so it's gaining momentum and becoming more and more interesting. And I'll put it here in this the presentation, the website darkmachines.org, and we also follow what happens in the application of machine learning to physics and astronomy with this Twitter account. Now, the last two things I wanted to mention is how you can exploit astrophysical and cosmological observations to search for dark matter, and how you can use gravitational waves. The first example that I would like to make is because there's a large community here interested in Gaia in particular. So I wanted to mention one way of testing some particle properties of dark matter with astronomical data, in particular with Gaia. So the idea is, well, I don't have to tell you that the Gaia satellite is producing extremely exciting results. There's a large community here, doing that, and this is really, the quality of the data is so spectacular that it's really transforming the field. One of the specific example I wanted to make in this to argue that astrophysical and cosmological observations in the future will transform the way we search for these particles has to do with stellar streams. So stellar streams are basically literally streams of particles, very cold streams of stars, very cold as a matter of fact, that are produced when, so if you have a galaxy, you launch a globular cluster, for instance, a big cluster of stars in the gravitational potential of the Milky Way. This cluster will get disrupted by tidal interactions and produce these very long streams of stars, almost unidimensional streams of stars. And we observe now, with Sloan, for instance, with the Sloan Digital Sky Survey, we have observed many of these streams. And the reason why this is interesting for dark matter is connected to something we have seen in when we looked at the numerical simulation of the growth of structures in the Milky Way. Let me see if I can go a bit faster on this. Remember, so we had this growth of structure that proceeds. But then if you look at what happens later, especially, throughout the history of the formation, this is the growth of a halo of dark matter, similar to the halo of the Milky Way. And you see that, this is time elapsed since the Big Bang. You see that the big gravitational well, so the halo, the dark matter halo of the Milky Way, is produced by the merger of many, many small structures. Basically enter the halo, they are stripped, tidally stripped, they deposit some of their material in the main halo, and some of these structures, especially the more dense, they will persist up to today, essentially. So one of the predictions of cold dark matter, so standard cosmology essentially, is that there should be many, many substructures of dark matter all the way to very, very small scales. So the current interpretation of dwarf galaxies inside the halo of the Milky Way is that these are the structures that you see in these simulations with a mass of 10 to the 7, 10 to the 8 solar masses. But then if you look at smaller masses, in principle it should be possible, these structures should exist down to subsolar masses. Then it depends on the particle physics model. It could be 10 to the minus 10, 10 to the minus 4 if it is supersymmetric dark matter and so on. But the prediction is that there should be more substructures in the Milky Way on the scale below the scale of dwarf galaxies. Now, how do we search for these substructures? Well, if you have this stream, remember we had these streams in the previous slide, and if you put now this distribution of this disk of stars and gas and the stream into a large potential where you have a lot of these small substructures, you can search for the interactions, the gravitational interaction of these substructures with the stream. Okay, so this can produce gaps in the stream, or in any case perturb the otherwise rather uniform distribution of stars in this stream. Now, this has been done using Gaia data recently. So there's a paper, for instance, by Harvard group that has basically mapped the position and proper motion and position of the stars in the longest stream that we have in the galaxy, which is this GD1 stream. And if you look carefully at the stars, you will see, even by eye, you see that they're not uniformly distributed. There are fluctuations in the density, and there are even clear gaps where you have very little, very small number of stars. Now, you can do a lot with this, and in particular, you can ask the question: is the inhomogeneity, basically, in the distribution of stars, compatible with the amount of substructures of baryonic substructures that we have in the galaxy, or do we need dark substructures to produce this amount of inhomogeneities? And this is the question I've asked this bright postdoc in Amsterdam, whose name is Neil Bannock. We've been working with some of the experts in the field, Joe Bovey and Dennis Helko, and we hope to have the paper out soon, though it's not clear when exactly. But this is basically the power spectrum of these anisotropy. So this is not anisotropy, inhomogeneities. So this is the question, have some departures from a homogeneous distribution of density in the stars as a function of the angle. And what you see is basically that these are the data obtained with a comparison, using Gaia data, essentially, of this power spectrum, this measurement of how inhomogeneous the distribution of stars is. And this is the amount that can be explained in terms of baryonic structures, so molecular clouds, globular clusters, spiral arms, and so on. So you see that there's quite a long way between this prediction of baryonic structures and this, which is where the data are. Whereas if you just take the amount of dark matter from a simulation and you just drop it on this plot, you see that the prediction of cold dark matter subhalos is able to go all the way up to these data points. So we think, if this is confirmed, that this is a hint of the fact that we are observing the perturbations induced by substructures, by dark substructures with a mass of order 10 to the 6 solar masses on GD1, on the GD1 stream. Okay, last thing I want to mention is gravitational waves. This is, again, like a field of research, so I cannot possibly make justice to all of it, but I want to show you at least one example of the exciting things that you can do for dark matter with gravitational waves. So the idea is the following. Well, you've all heard about gravitational waves. There's been a discovery announced in 2016, Nobel Prize assigned in 2017. And you've all heard that there's evidence of many objects, many black holes with a mass of the order of 10 solar masses that have been observed, merging with each other with gravitational waves. Now, in the 70s, Stephen Hawking, in the early 70s, Stephen Hawking was interested in these so-called primordial black holes. So black holes which were produced which were formed in the very early universe. So not astrophysical black holes produced by the evolution of stars. And he actually made the connection back then between these black holes and the dark matter problem as it was understood in the early 70s. So this is even before we had convincing evidence of dark matter from rotation curves of galaxies. And you see, astrophysical black holes cannot be the dark matter because, astrophysical black holes, they are produced by the collapse of baryons, right? So you would violate constraints that come from Big Bang nucleosynthesis and so on. But if you form these objects very early on in the universe, so if you make your baryonic number in a way disappear by locking all the baryons inside black holes, they can be they can be dark matter in principle. And what has happened in the past a few years after the LIGO detection is that people have been busy, putting constraints on this possibility. So this is a plot showing the fraction of dark matter that can be the form of black holes as a function of the mass of these objects. Now, for those of you who are familiar with this plot, I think for each of these curves we could discuss for a long time, but I think it's fair to say that for virtually all the range of masses, you have constraints that disfavor the possibility that all of the dark matter is in the form of primordial black holes, with the exception of these small window here, small masses, where these constraints become less reliable and less stringent. So the question I want to ask, and this is the last thing I want to mention in this talk, is can we detect these primordial black holes? Can we build convincing evidence for the existence of these primordial black holes with astronomical observations and with gravitational lensing? And what happens if we discover these objects? Now, the answer to the first question, I think, is yes. And one way of discovering and proving the kind of primordial origin, or at least the exotic origin, non-astrophysical origin of the black holes, with something that we can do now, really, without waiting for a too long time, or in the near future, let's say. Well, this is something we can do already now. So now there is, so the LIGO and Virgo observatories, they are in the observing run 3. So they are collecting data. They will be collecting data for the next year or so. And there are actually many tentative detections that have been already communicated to the astronomical community. They are still waiting to be verified. But the point is, suppose that you detect with this observing run 3, you start to detect subsolar objects, right? Suppose that you observe the collision of objects with of black holes with a mass of 0.5 solar masses. Okay, so there's no known channel in astrophysics to produce objects of this type. So even if a black hole is a very simple object, right? There's no Hare theorem that tells you, it's only characterized by its mass and angular momentum, essentially. Well, there's also electric charge, but just by looking at this doesn't mean that if you look at the mass distribution or the redshift distribution of these objects, you cannot learn something about their origin. So this, in my opinion, would point to an exotic origin of these objects. Another possibility would be to detect massive, like 100 solar mass objects, a very, very hard redshift. So if you observe 100 solar mass, the measure of 100 solar mass objects at a redshift of 40 with the upcoming ICCUB telescope, for instance, this again is something that astrophysics would really, it's virtually impossible to do with astrophysics. So this would also point towards an exotic origin for these objects. And then we've been studying in Amsterdam the possibility to use the square kilometer array to search for these primordial black holes towards the center of the galaxy by observing their radio emission. This is a bit more tricky. I'm happy to tell you more about this, but because I wanted to establish a connection with gravitational waves, if you think about these two scenarios, I think we can build up, in principle, a convincing evidence for the existence of these objects. Now, what if we discover these objects? What does this tell us about the dark matter in the universe? Now, the thing is, if these objects, so we've seen that, at least if you have like one solar mass object, or primordial black holes, they cannot be all of the dark matter in the universe. If they're not all of the dark matter in the universe, then they would, act as gravitational seeds around which dark matter over densities will form. Okay, so you have objects, and then you have, like a primordial black hole. And then you can study how dark matter would accumulate in these around these objects throughout the history of the universe. And there's quite a lot of work that has gone into understanding how this process would proceed. And even more recently, in January, there are people who perform numerical simulations that provide a very good match of the theoretical prediction of what would be the dark matter distribution around these objects. But now the interesting thing is, and the last thing I want to mention, the interesting thing is, if this is true, if it's true that you can form these large concentrations of dark matter around primordial black holes, then if this dark matter is made of stuff that self-annihilates, like WIMPs or things like that, then they would produce a very large flux of secondary radiation. The annihilation rate is proportional to the square of the density, and the density around these objects it can be incredibly high. Okay, so they would produce a large flux of gamma rays, synchrotron radiation, neutrinos, and so on and so forth. And the bottom line of all this is that suppose that you observe one system where you have the merger of 100 solar mass objects with the Einstein telescope in 10 years from now, when the Einstein telescope starts to take data. And I will show predictions between when this number of detections is 1 or when this number of detection is 24,000. Then you can set a constraint on the particle physics of these particles, in particular on the annihilation cross-section versus the mass of dark matter, of particles that self-annihilate. And this is a very busy plot, but what I would like you to get out of this is that if you take a supersymmetric scenario like this one shown in this shaded area here, right? This is the predicted value of the annihilation cross-section and the mass of neutralinos in supersymmetry. So this is where supersymmetry tells you that new particles could be. And you see that basically you could rule out with these experiments, with Einstein telescope, observing 1.3 and SKA, you could rule out basically the entire parameter space of these theories. So if you observe, even in the cases where dark matter is not supersymmetric, where these particles contribute only a small fraction of the dark matter, general supersymmetric scenarios will be ruled out by the discovery of primordial black holes. Okay, so this is really striking, and this is an additional reason to search for these objects. Now my time is up, so we'll skip this final comments that I had, and let me jump to the conclusions. This is clearly a time of profound transformation in the field of dark matter. In view of, as we say, the absence of evidence of most of the candidates we've been searching for a number of years. Although the absence of evidence is not evidence of absence, I think and in particular I think that LHC and direct detection experiments deserve to be continued because it might still reserve surprises. I've argued that we need to diversify these searches and to exploit astronomical observations and gravitational waves. And in general, especially for the young people in the room, I think this field is completely open, and there's really an extraordinary opportunity for the new generation of scientists to come up with new ideas and new discoveries. Thank you.
Thank you very much, Gianfranco. We have time for a few questions, if you want. Just raise your hand. Yes.
Yes, I have two questions. The first referring to what you said regarding the parameter space exploration using machine learning algorithms. So in this case, what sort of training sets do you use? Are these simulated data sets or mock or real data?
Yeah, typically you use simulations, and what you do is typically you calibrate your simulations on the data directly. Okay.
And my second question is, would you opine that we have closed the window to extra-dimensional theories, extensions, and hidden sector models of dark matter?
No, I don't think we've done that. I think we've set very stringent constraints on those theories, but the problem is that this applies to any class of theories practically. It's very difficult to rule them out completely, right? Because the parameters, these theories are extensions of the standard model. They have some free parameters, and the worst case is when you have full theories like supersymmetry, for instance, when you can have in principle more than 100 free parameters. So it's very difficult to rule them out. I think it's actually conceptually impossible to rule them out conceptually and completely, because you can always change the scale of supersymmetry to be a bit higher than what you've probed. The question, though, is how natural those theories are. Right? I mean, the reason why you postulate these theories in the first place is to explain the so-called naturalness problems, which is why there are so vastly different scales in physics. The Weak scale, the gravity scale, and so on. Now, when these theories were proposed in the 70s and 80s, the idea was basically I introduce them so I understand, and it becomes completely natural, from the theory that I can bring back some of the scales to be, to focus around the same type of scale. But then what is happening is that you're starting to push this, the scale of these new theories higher and higher, to the point that they are uncomfortably higher than the weak scale itself. So you have so you're introducing a theory to explain the naturalness problem, but then these theories become unnatural themselves. So instead of sticking too much to theories that you've postulated before, I mean, you can certainly do that, and it's quite obvious that people will continue to do these searches at the LHC and with the red detection. But what I argued here is that because we are getting more and more precision data from astronomy and from cosmology and from gravitational waves, the idea is to try and play the opposite game, so to try and learn as much as possible from the data and to be less guided by our theoretical prejudice, basically.
Thank you.
Yeah, the question? Questions? Well, I have one question. So if nobody else. So the mechanism, there are the WIMPs and there are the axions. This is what we understood as particles. So because what is the difference between them is that one is produced thermally and the other one basically are there forever. Are there any other mechanism of other particle that
for the production in the
for the production? Yeah.
Well, yeah. For the sterile neutrinos, you have very different type of mechanism for producing them. There's also this what people refer as gravitational creation, like in the case of these WIMP-Zillers. There's all these papers by ICCUB and Briotto and others for gravitational production, and then yeah, I'm probably missing some of them, but yeah, there are a number of other ideas that people have put on the table to explain the amount of dark matter that we observe.
Okay, so, okay, question?
Yes, a very basic question, I guess. You showed this pie where, from some time ago, I mean, you show it now and previously, and I hadn't seen that before. So there was no dark energy at all in the first pie that you showed. Is there any reason why dark energy is taking over? I mean,
that's right. I mean, what is happening is that what is happening is that as the universe expands, so for matter, the dependence of the density, the energy density of matter in an expanding universe is very simple, right? The universe expands, so the density decreases, linearly with the volume, right? Dark energy doesn't get diluted by the expansion of the universe. So what is happening is that the density. So you have initially you have the density of matter, which is up here. Well, first of all, there's the density of radiation, but let's go in the matter-dominated area. The density of matter is up here, and the density of dark energy is here. But then the universe expands, and as the universe expands, the density of matter goes down and down and down until you start to feel the energy density of dark energy. And that's, so you then continue to deplete matter, and then it becomes almost completely dark energy dominated. And that's what is kind of driving the accelerated expansion of the universe is precisely the fact that this energy doesn't get diluted, so you get this push basically.
Right, question there.
Yeah, can you comment a bit about these radio observations with SKA? How would this proceed, and what does it mean exactly?
Yeah, so let me see if I have some backup. I'll just check quickly if I have a backup slide about that. Otherwise, I'll just tell you in words and then dig it out from the paper. But the basic idea is maybe it will take me some time to find it. The basic idea is the following. Suppose that you have. So the first thing I thought when people started to argue that we could have all of the dark matter in the galaxy in the form of objects of primordial black holes with a mass of 10 solar masses, let's say. The first thing I thought is that's completely impossible, because even if I look at the bulge of the galaxy, where I know there should be like 10 to the 10 solar masses in dark matter, if this is in the form of 10 solar mass objects, we would have 10 to the 9 10 solar mass black holes in the bulge of our own galaxy. And then I can do accretion of gas onto these objects, calculate what is the radio and X-ray luminosity produced by this accretion, and show that it violates by many orders of magnitude the observational constraints. As it turns out, it's surprisingly difficult to set a stringent. It's surprisingly difficult to set a constraint based on this argument. The idea being that in order to do accretion which is substantial enough to produce an observable radiation, you need to have a density of gas which is large enough. And even if you're like 100 parsecs or several hundred parsecs above the disk, the density of gas is very, very low. So you don't get very stringent constraints. So the only way we could set these constraints is by looking at the small fraction of objects, of all these objects, which is inside the so-called central molecular zone around the galactic center, where the density of gas is sufficiently high to produce large accretion and then large radio and X-ray radiation. So we could set a constraint on the number of these objects at the level of 10 to the minus 2 or so in terms of relative abundance with respect to the dark matter, just by using Chandra data for X-ray and VLA data for the radio. But the point is that of course with SKA we're going to go down in sensitivity by a lot, and what we are hoping to do is that you can start to pick up a signal from these objects, even if they are a subdominant contribution to dark matter at the level of 10 to the minus 3, 10 to the minus 4, something like that. So it's not guaranteed at all to work, and there are, the reason why I wrote tricky is that, we've done the simple exercise of calculating how many of these objects we would observe given the sensitivity of the projected sensitivity of SKA. But of course, if you increase the sensitivity, you start to pick up many other sources. And then, the analysis becomes way more complicated. And that's, the part that I swept under the carpet. Basically, I didn't say much about that, but that will make the analysis very challenging.
You discussed a case in which the candidate for the dark matter particle is weakly interacting. Is the case that it's strongly interacting completely ruled out? I heard that this possibility has been recently reconsidered.
Do you have a particular scale of masses in mind, or because so until recently, so I'm not sure if I have something to write here, but you might have seen that the plot where you have the constraint on the scattering cross section of dark matter. But I actually have a version of this plot here that I can show you. Let me see if I can go here. So this is, I want to show you a plot where we have the scattering cross section on the vertical axis. This one here. Right, you have the scattering cross section versus mass. So whenever people ask, how do we make sure, how do we know that it is weakly interacting? One typically shows this plot and says, look, I've set a constraint, an upper limit on the scattering cross section, which is of order 10 to the minus 45 centimeters square. So strong interactions are like 20 orders of magnitude above that. However, what is rarely shown is that, this is it's true, it's an exclusion region, but there's an upper limit to the exclusion region. So if I showed, the whole parameter space up there, there will be a point, a cross-section above which these experiments cannot be sensitive. The reason being that, these particles are so strongly interacting that they start to interact with, either the atmosphere or the rock above the detector before getting there. And when they get there, they don't have enough energy to produce nuclei recoils that you can measure with your detector. Okay, so it's true that above a certain very, very high cross section, that you stop being sensitive to these particles. But then you can use other arguments because then you're really in the regime where the interactions are so large that you can start to have effects on the heating of the disk of the galaxy, because these particles really are interacting a lot for the whole history of formation of the Milky Way. And other constraints that come from special detectors that have been launched into space. And there's also a funny constraint that you can set on the heating. So this is a work that we've done many years ago, but basically we realized that if these cross sections are so large, basically these particles will start to interact with the whole Earth basically, and then slowly trickle down to the center of the Earth, and you would keep accumulating. So basically as the Earth moves around the sun and as the sun moves in the galaxy, you'll be basically this sort of a vacuum cleaner of dark matter particles in the whole galaxy. And you accumulate so many particles that their annihilation rate at the center of the Earth will be so large that it would exceed the heat flux that we observe coming out from the Earth. So that bit you can also rule out. So it's very, very difficult to reconcile unless you go to very, very large masses in tiny corners of the parameter space.
Sorry, maybe I missed it, but is this argument constraining the self-interaction or the interaction with?
This is the WIMP nucleon cross-section, interaction of dark matter with the nuclei. With standard
constraints
model.
of the self-interaction of matter with itself, with the dark matter with itself.
Right. So there are constraints. So the main constraints come from systems like the so-called bullet cluster, where you have you basically see that the dark matter basically clouds, they went through each other without interacting at all, essentially. And then, by comparing how much the gas has been shocked, that gives you an idea of the velocity of the collision, and how the fact that dark matter went through, you can derive a constraint on the self-interaction of these the self-interacting cross section. You wanted a number, maybe, or?
I thought that was order millibar over. So the cross section over mass was of order millibar over mass or something like this. That it was an order of hadronic cross section. That is the statement I remember.
Yeah, I can't remember that, but that might be right. Sorry.
Right. I guess we had many questions, but we have another one.
Yeah. Taking from the last question regarding self-interaction,
yep.
If I'm remembering correctly, one can impose some sort of velocity dependence using light mediators to evade this type of constraints that comes from the triaxiality of halos. What would be your comments on that?
Well, I'm not sure I have much to comment on that. I mean, yes, it's true. People have been playing with different types of cross sections, and in particular the velocity dependence on the cross section, 1 to v squared, 1 to the v to the fourth, and so on. And there's an entire community of people who are looking into constraints arising from how round the halos are, because this self-interactions tend to make these halos rounder. There are constraints coming from this merging system. There's also interesting constraints coming from as they call it, the swashing, I think, of sloshing of galaxies in gravitational potentials. The idea being that if you have like a galaxy, the argument is basically that the self-interaction cross-section could change how what happens in the inner parts of large dark matter halos, and that could change the dynamics of galaxies sitting at the center of these potential wells. So you're seeing how much these galaxies are, looking at the offsets basically between where these galaxies are and the center of the gravitational potentials that host these galaxies. You can also set constraints on the cross-section, and in particular on the different dependencies on the velocity.
Okay, so I think we can stop the question here. So before thanking Gianfranco again, so let me remind you that at 4 at the ICC room, there will be a meeting with Gianfranco and students, if they want to go. And at 5, anyone from postdoc or staff can come again in the same room to meet with Gianfranco. And now let's thank Gianfranco again.
Thank you.